So it's a good question. It's question number 22 from examples of HC Verma Volume 2 capacitors. I've been quite busy lately, so it's like very hard to. It's being this chapter is taking very long, but anyways. Uh, So what's given is that these are two conducting plates and a dielectric substance or medium or whatever you say insulator is put till some kind of a length x. It has a thickness of d and the separation is also d. The length of the plates is l and the width of the plates, if we are going 3D, this thing is b. Right. It's 3D. Let's go 3D actually. That this is also b. Now first part is, of course, the battery. The connected to some kind of a battery. It's providing voltage V, right? And of course, this voltage V is constant. The potential difference across these two plates will always be V. And first is the energy of the system when a length X is introduced. Of course, when they're using X, you just understand some kind of a differentiation or integration is involved in this part or some other part. So the energy of the system is given by half CV square. Otherwise, if you write C as Q by V, it's half Q by V times V square, which is half QV. You can also write V as like it was Q is equal to CV, right? You can write V as Q by C and hence it becomes Q square by C square. So half Q square by 2C. Or Q square by 2C, you can say simply. They've solved as this in the book. They've solved using half CV square, and I think it's the best method. So you have to find the capacitance of the whole system, and it's easy. It's just simply just ignore this part exists. You have this part inside and this part of air, and it can be thought of as two capacitors. Like this is one capacitor, this is another capacitor. This whole thing is one capacitor, and this whole thing is another capacitor. The K is equal to 1 here, like the constant, it's not 1 here. And it's some kind of a parallel connection. And why parallel, you may say? Well, since the potential across these two, of course, the potential across the wire is same. The potential is same. The charges are distributed differently. Potential is same, and like that is when we have parallel connection. So yeah, that's it. And let's calculate the capacitance. The first thing, this thing, we know it's A epsilon naught by D. We are assuming very large plates actually. So A here becomes B times X. A epsilon naught by D. And C2, and of course, do not forget the dielectric constant K. And it's again its length, that is it is L minus X to B L minus X epsilon naught by D, and of course parallel just add them in. We have B epsilon naught by ds common, and find with kx plus L minus X. And if you take X common, kx plus L minus X, L plus x k minus 1 will become the same. Kx plus L minus x. B epsilon naught, B epsilon naught by D L plus x k minus 1 is the equivalent capacitance. They have asked, of course, the potential differences is same. It's half CV square for both. That's why it's parallel, so it becomes half the energy, basically potential energy. So half C, which is, let me write it down, B epsilon naught TL plus XK minus 1 V square. So this should be your potential energy. Epsilon naught BV square upon 2D L plus XK minus 1. It's fairly easy if you ask me. Second part is good. They've asked us what the external force should be so that it moves slowly, meaning it should not change its kinetic energy. If it's initially moving for 0.02 centimeter per second, should move by that limit only. And if it was originally stationary, it should be almost stationary only. It should be so slow. If it moves so slow that it should almost be stationary or very slowly. So, of course, in this case, there should be no acceleration, so the forces must be balanced. Now, you may ask, of course, in a capacitor, don't we have the forces? Here they have asked to neglect gravity and friction, and the electric fields are perpendicular. So, how will it experience any kind of an external force in the horizontal direction? Well, it is it is perpendicular, of course, when it's completely filled with one material. But here we are making another material come inside, another dielectric material come inside. The electric fields won't be perpendicular. Of course, when it will be completely inserted, let's assume if the length is hole is L, if it becomes completely inserted, then the field lines will be perpendicular by symmetry. But now they're not. It's not symmetrical. So I found some kind of a diagram to illustrate that. So there are sigma and minus sigma. Of course, if there's some Q charge, there should be some minus Q charge, and like as sigma. And the electric fields are perpendicular. But when another dielectric medium is being put, look at how they change. Some kind of charges accumulate. What they call it? A bound charge? If I'm not wrong. Let me let me know. Bound charge. It's called the induced charge, and it's also called the bound charge. Okay, so I'll call it the bound charge. It's cool. So the bound charge appears and some kind of an electric field. Alright, so let's assume, just simplifying, there was a positive charge and there was a negative charge, and there's another negative charge, and a body consists of a negative charge and a positive charge. What will happen? This negative charge will be attracted by this. The distance between here is larger. It will be deflected, but by not that, of course. Of course, we're not talking about perpendicular. Uh-huh. But let's assume when this is reflected and it's attracted and there's some kind of a force. Lunar plates are large, but like just an approximation. Field lines will vary, something like this. And so it will feel some kind of an attractive force or repulsive, depending. I think it should be attractive only. It cannot be repulsive. But wait, let me see. Musk versus Trump. The big beautiful bill. That's the question. Sorry. Uh, wow, no, I'm not preparing for him. Was it? Huh. Found a good diagram here. This one. As long as the dielectric is nothing happens, or there's like not the charge on the induced, the field lines are modified, resulting pulls the dielectric, and it's some kind of a periodic motion, not SHM, some kind of a periodic motion also happens, right? We can also prove this by another way. If this we cannot think it this during the exam. Uh See the energy of the system, how much is it? Let's assume a small length dx is also being pushed. So how much is the change in potential energy? Of course, the change in potential energy will be the half dcv square. And how much will be the work done by the battery? If the whole configuration is taken as a system, what was the work done by the battery? The work done by the battery is of course it's VDQ, and DQ is also written by CV or DCV. So half DCV square is equal to mm, V square DC. And it's not possible unless and until the it's given some voltage. So there must be some kind of this is the potential energy, some kind of a kinetic energy here, which must be equal to just half dCV square. Must be some kind of a kinetic energy. Some we cannot be we are neglecting if some kind of a heat or sound is produced. So also some kind of a kinetic energy should be present such that it's balanced. So it can be proved that it will get some kind of an attraction. So let's find the force. Let me assume it's an attractive force. So we have to do an opposite work. Let the force be F. So we have to do the work done by the external is minus F dx. Work done by the battery is, as I already mentioned, VdQ. dq is CV. So V square dc. And this is equal to the work done by the batteries and internal force. Wait, battery, I don't think here is being taken as an internal force. Uh, wait, wait. One being internal conservative. That's the fun of it. Basically, I have to rethink my solutions, and that's why I'm making these videos. Uh, Wait, I think I'm getting something wrong. Mhm. Is this an internal force or what's the system? See, the thing is, the work done by the battery should be an external force, not an internal force. We do define the U as a half, or sorry, U as half CV square. It's the potential energy, but it's basically the potential energy due to the electric fields, the capacitor itself. It's due to the electric fields. That's minus of the work done by the internal electric fields to so that the plate is moved, for example, to some distance. Uh, right. This is some kind of a potential energy just due to this system, half CV square. It's just the potential energy due to this, the electric fields basically, of the system. You can say the system is making electric fields. See, the electric fields are taken as internal. So when we derive this thing, half CV square, how do we derive it? Let's assume a plate is moved by some kind of a distance. The work done by the external force should be how much that should be. It should be Q upon A epsilon naught, 2 A epsilon naught. Should be the and times G2 minus G1. And this whole thing is the net electric field. Not this. This is the capacitance, right? Capacitance divide 1 by capacitance, Q by 2C. And Q is also given by CV. What V by 2? Wait, something, something. The force equal to A epsilon naught times the displacement. Q can be written as CV. This whole thing can be written as electric field. Also, what's no, not the. I mean the force by the electric field. A epsilon naught is the capacitance. Like what I'm getting confused. It's the capacitance. You see what? It's half CV square, right? Cannot be V by 2. So square by Ah, no, I forgot. It's the electric field. Sorry, it's not the force. This thing is electric field. Forgetting electrocharts. Basically, I've been studying different things for too long. And I've started forgetting things. Oh no. So it's an electric field and we have to multiply it to get the force. And this is the net force. Completely forgot what I was going to say. So it's q square by 2c. और q is cv तो cv square half. One thing is capacitance c is equal to q by a epsilon naught by delta d. Yeah, it's delta d. So it's delta d, of course, so its capacitance is half cv square. Now, because it has we does not mean that the battery has become internal. Basically means we are not including the electrical. See, work done by external is a change in the potential energy if kinetic energy is not being changed. And when there are two plates, you are separating them. There are two forces on this plate: the force by the man and the force by the electric field. And since its kinetic energy is not increasing, the work done by the external force is zero. So the potential energy should be zero. But it's not. Because we assume this electric field is not external. It's an internal force. So electric field is assumed internal, right? Let me write that down. See, I do learn when I make explainer videos. Electric field is taken internal. Of course, it's taken internal. It's quite common sense if you look at it now. But I just missed the point. Never really thought about it. So electric field is taken as an internal source. So here too, we are taking the electric field as an internal force, right? So the work on the system, the work on the battery is external. You can argue that the electric fields is also made by the battery because we have the charges and charges come due to the battery. And let me think about the argument. Mm, See, work done by the battery here is different. Like when you say work done is equal to VDQ, what does that mean? What does that mean? Why is the work done VDQ? Basically, how we define the work done on electrons or the change in the potential energy of these electrons upon the charge is the change in the potential. That's how we define potential. Change in the potential energy of the electrons. Potential energy relative to themselves. Some kind of another electron. So here the battery is basically doing work as it's moving electrons. Not because of the electric field. Because the change and basically the change in the potential energy of the electrons is delta V Q. That's how the potential is defined as the work done for the charge from making it from some point to another point without raising the kinetic energy. Now, see, you can also write it as another way, not the external forces. You can make two equations. First is you can assume the battery to be doing an external work, the battery to be doing external work by moving these electrons. And you can say the work done by the external forces minus f dx plus v square by d, so v square dc is equal to half dc v square. First, you can make the equation by this way. The second way to make the equation is you can say the work done by the external force. You can include the electrons in the system. You can say the work done by the external force is the change in potential energy, the final minus initial. So half dc v square and the change in the potential energy of the electrons. The electrons, the change, of course, is negative because when they're moving from a lower potential to a high potential, that is from a higher potential energy to a lower potential energy, of course, it's the change is negative. So how much that is? It's basically they are the final is potential is zero. And these electrons initially they were at some kind of a potential or potential energy, and it's this thing charge. You can take that into the like take that to the other side. VQ, of course, we are talking about small charges this time. So DQ, this small instant where some small charges, and the equation is and DQ is equal to DCV, and the equation is basically the same. We have just taken this V square DC here and becomes 0 minus V square DC. This is different. It's the mode and my external forces. If capacitor and electric field are taken as a system, and it's basically the mode and by external forces equal to the change in potential energy if these electrons and the whole circuit is taken as system. This is the same equation to solve them. Achha. So just solve it. It becomes a half V square DC is equal to FTX. And F is basically DC by dx V square, half V square. And we know the capacitance. It's epsilon naught B by D L plus xk minus 1. We just calculated that. And so let's put it in. Let's differentiate the constants. They come at front. So this of L is 0 and of x k minus x. Well, of xk is k and of minus x is minus 1. So k minus 1. And that's it. Epsilon naught bv square. Epsilon naught bv square k minus 1 by 2d. It's the answer. It's the force, the external. So that it does not change its kinetic energy. Epsilon naught bv square k minus 1 by 2d.